Hello and welcome to today's SGIA webinar, Driving the Future of Color. My name is Dan Marks, SGIA's Director of Industry Content, and I'll be moderator for today's program. On behalf of SGIA, I'd like to welcome you and let you know our webinar system allows you to ask questions through your computer. So if you have questions at any time, feel free to submit them, and we'll get to them at the end of the formal presentation. Before we get started, I'd like to introduce today's speaker, Max Derhak. Max has worked for Onyx Graphics Incorporated since 1990, where he currently functions in the role of principal scientist. Max has a bachelor's in computer science from the University of Utah, a master's in imaging science from the Rochester Institute of Technology, and a PhD in color science from RIT as well. He was an initial contributor to the open source Sample ICC and ICC XML projects, which he continues to maintain. He serves as a co-chair of the ICC as well as the chair of the ICC Architecture Working Group, and has been a primary driving force in the ICC MAX project and its reference implementation. So without further ado, I'd like to introduce Max Derhak. Max?
Thank you very much. This is a topic that I really enjoy talking about, and hopefully you'll learn something and be able to appreciate the beauties of ICC color management and the extensions that we're adding to it. So to start off, let's talk about color management and what it is. Now, I like to define color management basically as being related to answering various questions about color. We can talk about what it is. You can talk about how it's formulated, controlled, or made. We can talk about what does it look like and how does it relate to or interact with light. These questions have some key components related in color management. First of all, is we can talk about formulating these questions, providing answers for these questions, and then communicating everything. And in creating a color system, system for doing color management, really basically, it's really how you basically can formulate these questions and answer them and communicate. How basically all of that is involved in basically creating a system for color management. Now, let's talk a little bit about basic color reproduction. Say we have ourselves a lovely little monitor and a printer, and we're going to take an image in which that's a proud moment in my life. I can see the image from what I took from my camera, and I want to print it out. So what we're going to do is we're going to basically consider asking questions and answering those questions to basically perform the color management and see how color management actually fits into that. So the first question is, well, how much ink is really needed to match pixels on the screen? Now that's a loaded question. There's a lot involved here. There's basically what's on the screen, there's inks and stuff like that. Now we can take that question and we can kind of divide it into two separate questions. What we can do is we can say, so what does a individual pixel, RGB values, what does it look like? And then based on what it looks like, then how much of CMYK ink do I need to print in order to get the same look? Now, the word look here is the critical thing here, because look is really basically associated with color perception. You know, it's basically involved with, you know, how we perceive the color to look like. And we're going to talk a little bit to understand this about what goes into color perception. Now, color perception is a fairly involved thing. Color itself is actually a fairly involved thing. We think oftentimes color is being simple because we see it every day, but there's different ingredients that go into getting color perception. You first start off with a light source. Now, the light source may be a light bulb, it might be something on the screen, might be the sun, and that light source is either going to be directly viewed, or the light itself will interact with other objects in some fashion and then make its way to the observer. Now, the observer himself or herself has light sensors in the eye that convert the light energy into a signal that gets processed by the brain. And it's really basically at the point where we actually get inside of the brain where we end up having perception. So basically, you know, understanding color actually ends up being something of a neuroscience kind of thing that goes on. Now, color itself has spectral aspects. The light itself basically emits light at different varying wavelengths, from short wavelength lights, which are made up of blue, up to long wavelength lights that are made up of red. And basically the distribution of the wavelengths of the light determine basically the characteristics of that light source. And different light sources have different characteristics, spectral reflectances. Now, the light at the different wavelengths then interacts with objects. Now, the objects themselves also interact with light at different wavelengths, either absorbing or reflecting to some extent each one of those wavelengths. A gray object will actually reflect light that's basically in a fairly consistent for all wavelengths. The light itself then gets reflected off, and then you have the sensors in the eye, and they themselves are sensitive to different wavelengths of light. And what this really means is that you can have different objects and different light sources that will appear the same, because the signal coming from the cones, which basically integrates those wavelengths that are passed into the brain, actually end up being the same. Now, to really work with light, we need to actually come up with a way of quantifying what's going on in terms of perception. And so in the 1930s and experiments leading up to that, they defined basically standard observer color matching functions that basically just define essentially the sensitivities at various wavelengths for three signals: the X signal, the Y signal, and the Z signal. Roughly correlated RGB, but not necessarily red, green, blue light. Now, you can basically take that information, and then you can plug it into a really nice formula. I'm not going to go to great detail, and you don't necessarily need to understand it. The real key is that basically by using this math, we actually end up with the ability to define color perception in terms of three numbers: capital X, capital Y, capital Z. And basically the idea is that if you have two colors that give you the same XYZ under the same kind of viewing condition, the colors will look the same to the observer. Now, to give an idea of sort of what's going on with all this spectral stuff, you could basically take into account the spectral reflectance of, let's say, something that looks kind of orange. Now, you can basically take the daylight illuminant and basically take the product of those two, and then basically you can see the light that would be reflected off the surface under daylight. Under a fluorescent light bulb, F10, this fluorescent light bulb that has basically the same sort of appearance, the light coming off the surface is dramatically different. Then if you basically integrate that with the different sensors, the X, Y, and Z sensors, you can see basically the light involved with those sensors, and basically the area under the curves there is basically going to give us essentially the measure of the X, Y, and Z values. And so basically the color values themselves basically correspond to a sort of amount of light that's seen by each one of those sensors. Now, we take those XYZ values, they can tell us whether the two colors match, but they don't necessarily really give us a good idea of sort of how things are perceived. And then additionally, one of the aspects of the coordinates of XYZ values, if I have a distance between two XYZ values in greens and a difference in XYZ values in blues, the perceived difference in those colors will not necessarily be the same for every possible color. And so in the 70s, the CIE developed a transformation of XYZ values into a coordinate system that is more perceptually uniform. And it's defined in terms of XYZ. It has three axes. You have an L axis that defines basically lightness, and you have basically an A axis that goes from red to green, and a blue axis that goes between blue and yellow. And basically doing combinations of the of A and B give different kind of hues. And basically the center, when A and B are both 0, kind of defines a neutral grayscale. Now, one thing to note with this is that because this right here is essentially dividing by the XYZ value of the illuminant itself, CLAB will always give a value of 100.00 for white, regardless of what the illuminant is. And so if we're looking at things under, you know, daylight or things under an indoor light bulb, the LAB value is the same. But that doesn't necessarily mean they appear the same. Now, getting back to those color management questions, rather than just using the kind of the fuzzy word look, what we can do is we can actually use quantified value, quantification for what it looks like in order to do the color management. And so basically in answering how much ink is needed to match pixels on the screen, we can basically say what XYZ or lab value does this RGB pixel have, and how much ink is needed to get the same XYZ or lab value. And so by having quantification, now you actually can define the color rather than just a fuzzy, well, it's brown. You can say that it's a specific XYZ or lab value. Now, the ICC profile specification basically uses these XYZ and LAB values to define basically a system for answering questions and doing color management. It was standardized as an ISO standard 15076, which defines the version 4 profile. It defines a standard container or a file format for defining color management. It's widely used around the world. It's predominantly used in graphic arts. And it was first published in 2005, and it's been very successful in spreading color management to many parts of the world. Now, if we want to look at that question, we can basically look at that question actually in terms of how it's implemented in terms of a color management module and ICC profiles. So you have an input profile associated with a monitor that basically answers the question, what XYZ or lab value does this RGB pixel have? And then the CMM internally understands how to convert between X, Y, Z, and lab. Those are basically standardized equations. And then the output profile converts from a lab value to CMYK, answering the question, well, how much ink is needed? Now, how you go about doing that is basically defined by rendering intents, which define the use of different transform tags in ICC profiles. Now, transforms in ICC profiles, this gets into a little bit more of the detail of what's going inside of a profile, are basically made up of processing steps which have data elements in the profile. And for an input profile, you can basically independently adjust the individual channels. So for CMYK, it would be independently adjusting the RGB and value, or CMYK values, or RGB for a monitor. You have an n-dimensional lookup table, which basically is a table that basically answers the question of, for a given combination of input values, what is the output value? And you have every possible combination with at certain steps, and then the CMM will do a lookup inside of that and do interpolation between the values to figure out values that you don't have in that table. And then you can apply lookup tables to the results of that, a matrix, and then individual sets. This right here basically has the actual transforms that are just prescribed for version 4 ICC profiles. And for input profiles, the output profiles basically does things in reverse order, and device link profiles, which basically going for device values to device values, are the same. A PCS is a profile connection space, which is basically the XYZ or LAB color space that I described earlier. Now, ICC version 4 profiles are very successful and very useful, but there are limitations to using version 4 profiles. The first thing is you have a limited ability to answer the question, what does it look like? The profile connection spaces are only defined in terms of a single light source and observer. It basically uses the D50 or daylight illuminant for the standard 1931 2-degree observer. And so it's only basically describing color in terms of one kind of experience that you have. And this means that you really can't necessarily describe how color changes due to lighting or looking at things from different angles. Another assumption is that basically you're talking about matte surfaces, where basically it looks the same regardless of what angle you have the light coming in or what angle that you're looking at it. You're also very limited in your ability to answer what is it. You know, basically you only have that sequence of processing steps you can do, and if you need to do something else, you can't necessarily do that. Finally, you're not necessarily able to basically really describe how it relates to or interacts with light, because basically it's only defining color in terms of the perception, the XYZ and LAB value, and everything involved with the lighting or how it interacts with the surface or how the observer actually senses the light are basically all kind of wrapped up into the XYZ equations, and so you can't untangle that and be able to describe sort of those light interactions. Now, because of this, ICC version 4 can be very restrictive, and one example I'm going to give here is basically packaging printer. And in this case right here, what we have is basically CMYK process colors with some additional spot colors. The spot colors may actually have gloss or metallic inks, and there's some challenges here. First of all, the version 4 lookup table structure is really not practical beyond 6 or 7 colors, because the profiles get really, really large and the processing gets really, really slow. And if you really want to basically do this in the packaging industry, they found that they need to actually spectrally define the spot ink color so that basically they can format the inks to get the same look under any lumen. Okay, and you can't define the directional appearance of the ink in the profile. If you have metallic colors, you know, you can see where they have the gloss. If they actually, you can actually print with a glossy varnish, and that necessarily can't be described in an ICC profile. So really basically, you really can't describe how it will look under a variety of different observer and viewing conditions. Because of these limitations within the ICC MAX, within the ICC community, we began developing what basically became ICC MAX as a 10 years process to basically define new ways of doing color management that allows us to basically address things that are either not addressable or difficult to implement using existing ICC version 2 and version profiles. In doing this, we still wanted to actually provide open cross-platform vendor neutral solutions. We wanted to have it as a result of this, being able to allow ICC color management to be used in new industries like medical imaging or fine arts or satellite imaging and things like that. As a result of this, we've defined specification documents and a reference implementation. So I'm going to talk a little bit about this. Now, to get a kind of an understanding of what the relationship between version 4 and ICC MAX, you can think of ICC version 4 as basically a basic kind of Lego building block where you have ICC version profiles. The specifications provide the basic building blocks for defining and implementing a color management workflow. And with ICC MAX, what we've done is we've basically added additional building blocks and capabilities to the CMM that allow us to basically answer more complex questions and answer them, all basically maintaining some backwards compatibility with version 4.2 and version 4 profiles. Basically, you can connect these version ICC MAX and version 2 profiles together to actually get color management solutions. Now, because ICC MAX defines a large collection or adds a lot of additional things to color management, it provides basically a platform for defining specific color management workflows. And so each workflow may actually only necessarily need to use just a small subset of basically the entire ICC MAX specification. And basically these subsets are defined using interoperability conformance specification documents. Now, an ICS is like defining a smaller kit from the master set of building blocks. You know, in Legos, you know, you can buy the huge kit that has everything, or you can buy a kit that just has all the pieces you need to do just a specific thing. So if you want to make a truck or a claw thing that picks stuff up, you know, you can define basically the things that you need to do that. Now, products that really want to implement aspects of ICC MAX will basically choose which ICC workflows they support. It's not necessarily just designed so that basically ICC MAX is going to be implemented everything everywhere. It's basically you pick and choose the pieces that you really necessarily need. This basically allows for ICC MAX to be extended so that we can potentially add additional building blocks without necessarily damaging or making things difficult for people who have built products based upon ICSs that won't necessarily use those extended building blocks. Now, if you look at the building block overview of ICC MAX, there's a lot of stuff in here. And this right here is not a presentation about all those blocks and how you can use them and all that stuff. That's something we would do in something like an ICC Developers Conference. But overall, basically, there's 4 kind of basic categories that I would actually block them into. You have color space extensions where we can do things with spectral stuff and keep track of and understand how to deal with light. We have multi-processing elements that basically expand how we can encode transforms with various programmable elements to basically achieve or communicate about how to transform between device and various profile connection spaces. We've extended it so that the structure internal to the ICC profile has been extended to be hierarchical, to give us basically the ability to add to it without necessarily having to create fundamentally new complex without having to actually modify the parser to be able to do it, similar to something like XML, but in a binary fashion in ICC profile. And there's other extensions that basically give a allow us to do different features and capabilities. So rather than talk about, I'm sorry. Now there's 2 representations that you actually have for ICC MAX. ICC MAX is the actual specification. It basically extends upon basically the whole format of version 4 with a binary header and tag structures. And this provides a very compact format for embedding and computing about color. In addition to this, basically the reference implementation also provides tools to convert between the binary representation, the kind of thing that you would put inside of an image or a PDF file, and an XML representation, which is basically text-oriented, which basically is human-readable and modifiable. And the nice thing about having an XML representation for profiles is that basically, in some cases, complex tools are not necessarily required to create ICC MAX profiles, because you can basically create an ICC MAX profile as a color transformation program. So, rather than going into details about ICC MAX, what I'm going to do is basically do kind of a Q&A. What are sort of questions that we can then, because color management itself is about asking questions and answering questions. Well, what questions can we answer using ICC MAX that maybe you can't necessarily answer using version 4 profiles? Well, let's talk. The first one, basically. So this is basically a kind of a slight shift from the questions that we were talking about initially. So what XYZ or LAB value for a particular observer under a particular luminant does this pixel have? And what device values are needed to get an XYZ or lab value for a particular observer under a particular luminant? This right here basically allows different light sources and different observers to be used in terms of the color management. You're not limited to just using a standard D50 illuminant or the 2-degree observer. And so another question, what is the XYZ or lab value for an RGB pixel that has a specified color encoding space? One of the things as we're getting ready to do ICC MAX is we had the camera manufacturer come to us and said, hey, you know, we just want to basically have an image that has RGB values, and these RGB values are all going to be sRGB. We don't want to communicate how you transform the colors. All we want to do is basically define what the encoding space is. And so ICC MAX has colored space encoding profiles that really only contain basically a header and a tag that says, hey, I'm sRGB. And then it's the ICC MAX CMM that has to figure out what the transform to use that's appropriate for doing that. The transform is appropriate for basically converting the pixels. Next question. So how do I convert XYZ lab values for one observer illuminant to XYZ lab values for a different observer illuminant? Now, with the ability to potentially say, well, I'm going to start off with something that's under a light bulb, you know, in the house, and I want to figure out what it's going to look like outside, or vice versa. ICC MAX provides basically the concept of profile connection conditions, and these are basically in tags and header entries in the ICC MAX profile that basically provide transformations for a CMM to make conversions when they're needed. Now, these conversions can use a more advanced color appearance model, or it can use basically a material adjustment transform to actually do that adjustment. Now, material adjustment transforms are actually based upon color equivalency representation that basically was part of the basis of my PhD dissertation. And on the side, you can basically see here that basically the normalization itself basically takes the XYZ values from different viewing conditions and basically adjusts them into kind of a lightness chroma hue thing that really basically has good alignment. It gives basically then provides a very good prediction of how a material color will change for different observers and or illuminants. Next question. Well, how is light absorbed, reflected, or transmitted by a surface with a specific device phase? What device values are needed to get light absorbed, reflected in a specific way? And how do XYZ values change as the observer and or illuminant changes? These right here basically factor into the idea of using spectrally based color, communicating about color spectrally, as opposed to in terms of XYZ or LAB values, which really basically are how an observer perceives it. And so basically things like reflectance and transmittance can be described. And the ICC MAX CMM allows basically the observer color matching functions to be described, or the spectral power distribution of the light to be factored in to computations in order to answer various questions. You can basically connect things and find out the spectral reflectance of an object and not worry about how an observer sees it. It's independent of the light source. The one key with this is basically you can, in basically doing color management in terms of the printing world, if you want to use different light sources or observers, that has to basically be pre-computed and then converted into how it appears to the standard observer under D50, and it's fixed at the time you build the profile. With the ICC MAX based CMM, using the observer and the light source can be deferred not when you apply the profile, as opposed to when you build the profile. Well, now since we actually have spectral stuff, we have to be able to actually ask the question, so what if I want to actually do everything in terms of a spectral reflectance? I want to do profile connection space with spectral reflectance. Well, how do you manipulate spectral reflectance? Now, characteristic spectral reflectances can be associated with, on a hue basis, with WPT coordinates as described in my dissertation, and then a very simple linear method can be used to estimate and manipulate spectral reflectances. What this really means, though, is that ICC MAX profilers can then basically do things that they do normally with XYZ and LAB, but do it with spectral reflectance, to do spectral gamut mapping, spectral color rendering, adjustment of abstract profiles, adjustment of spectral reflectance using abstract profiles, or you can basically have an RGB data directly estimating spectral reflectances. Here's a question that I'm sure everybody here is has always had on their mind. How is reflected light affected by the use of a substrate with optical brighteners or printed using fluorescent inks? And really the key here is that basically in some cases light, when it comes in contact with the surface, is absorbed and then re-emitted at a different wavelength. And so things like a spectrophotometer, when it measures it, doesn't really understand that the light actually changed. And the CMM itself, maybe based on that, doesn't understand that. And one of the key aspects that's really made a mess of the printing industry is the use of optical brighteners. Optical brighteners are used by paper manufacturers to make the paper appear brighter, because it's basically converting the UV light into blue light, making it look brighter. And so ICC MAX provides basically support for basically modeling and handling and characterizing how fluorescent works. So how do you handle lots of device channels without having to agree about the algorithms used? Now, the real key here is there's two aspects to this. With ICC version 4, since everything is based on a table, if you really have more than 7 dimensions, you end up with having a really big table. ICC Max doesn't require everything be done in a table. ICC Max has multi-processing elements that basically allow you to program the transforms. So rather than basically doing a multi-dimensional lookup table, you can put in an algorithm in there that basically defines how to actually adjust it, which doesn't require a whole lot of storage space and will also potentially provide more accurate results, especially when you have lots and lots of device channels. And below here is sort of kind of a collection of some of the processing elements that one can use when implementing an ICC Max profile. So how does reflected light change as lighting and viewing angles change? You know, ICC version 4 assumes matte. I mean, basically, we expect that the color doesn't change when you look at it from different angles. But in all reality, color changes a lot. The texture of surfaces, I mean, if you print out something on a glossy media, if you look at it, you can see where the light's reflecting off the surface. And if you actually have things like metallics or things with flop colors, you know, changing the angle can dramatically change it. It's not just a reflection of the light, but basically the particles themselves reflect the light differently and will change the hue from blue to pink or red to green. With ICC Max, the ability to basically characterize how light interacts with surfaces, not just in terms of reflectance, but also in terms of viewing and lighting angles, is a possibility that can be incorporated within an ICC Max profile and a capable CMM that uses that. So what is the spectrum of light coming off of the display? You know, we talk about RGB displays, but in all actuality, the light coming off the display is multiple wavelengths of light, and different displays will actually emit light in different ways. If you think of an LCD display, it basically uses an LED backlit with some color filters to get the output. New quantum dot displays, they basically end up with emission spectra that are very spiky. It gives the ability to get really wide gamuts. But one of the challenges with using such displays is that because they have narrow selectivity in the output wavelengths, that narrowness will interact with variability in observers. Basically, normal non-colorblind observers in the populace have variations in how they see things, and those narrow wavelength monitors will actually end up making things appear significantly different to different observers. Now, if you're using one of those monitors and you're doing very color-specific color-critical manipulations, you need to potentially actually have color management that takes into account how the observer who is looking and using color management sees things, so that basically you can account for the variations in how the different observers perceive the color. ICC Max provides essentially both the spectral modeling of the displays as well as applying observer-specific sensitivity functions to really basically do color management with such displays. So how does light from a video display change due to position and angle? I'm sure many people have observed the monitor technology has improved dramatically, but if you basically look at your LCD monitor at various angles, and especially if you go from top to bottom, you can notice that basically the color on the display dramatically changes. And one thing that could possibly be done is you could put basically a motion tracker on the head to basically sense where you are and where you're looking at, and basically provide color management that basically accounts for how light is changing for what you're seeing on the display. ICC Max provides basically support for both doing the characterization as well as modeling that. How is light reflected by tint of a name color? In version 4 and version 2 profiles, you have named color profiles. Named color profiles are kind of a different class of profile. A different class of profile that basically provides a name and then an LAB value for that color. So you could basically define Pantone colors, and so for Pantone 402 I have the LAB, and for the Pantone 403 I have the LAB. But it's limited to basically solid colors. With ICC Max, we've extended the ability to basically work with named colors in multiple ways. In addition to output device values and XYZ lab values, you can define reflectance and transmittance or fluorescent values. You can define the opacity and overprint characteristics of it. So for spot colors, you can find out sort of, is it opaque or is it transparent? Additionally, you can define how light changes by viewing and observing angles. So you could actually have named colors that have metallics, and you could describe how the metallic changes under different viewing conditions. And the one other key aspect of it is you can do it on a tint by tint basis. So rather than just doing solids, you can define it for 10, 30, 70, 100%, and then interpolation is used to define intermediate values for all of these characteristics. Okay, another question. What is the probability that the pixel of a multispectral image contains a specific material? And this basically allows a completely different way of thinking about color. ICC profiles really describe things in terms of what does it look like. ICC Max also gives us the ability to know how does it interact with light. But in some cases, what you really have is you really basically have image pixel data, multi-channel stuff, that basically is sampling at various different wavelengths under different conditions, and you're going to want to combine those to not define what does it look like, but define sort of what is the probability that it's something. So like in the medical imaging, this would basically defining biomarkers. So what is the probability to have a biomarker here based upon all this input that I have a cancer-causing I have a tumor? Or you could talk about satellite imagery, where basically the pixel information is being combined to basically determine the probability that it's roadways or grass or trees or buildings. In the fine art industry, you're basically taking your imagery coming in, and what you really want to know is basically an estimation of the pigment concentrations for and which basically then provides the ability to determine how to make conservation, or they're going to retouch it, or to fix problems due to the aging of the fine art. Now, ICC Max basically provides a new connection, a way of doing connection, which is based upon basically defining color in terms of what it is, as opposed to what it look like or how it interacts with colors. And these kind of workflows are possible with this. One thing for the packaging industry is basically defining in terms of what is the ink amounts. So last question, how does ICC Max help with package printing? I kind of basically said that, with version 4, you kind of hosed there. With ICC Max, well, we can define the spot color spectrally. Any number of colorants are supported using programmable processing elements, which allows the estimates of spot color overprints. And I've demonstrated in ICC meetings, having an 18-channel ICC profile that gives the ability to use any of those 18 colors and do a emulation of the overprinting. You can get a preview of directional effects of gloss and metallic inks. And with this right here, we basically can define how things and give previews of how this package would look under different viewing conditions by applying different illuminants or observer changes or doing a 3D rendering on the monitor. So, kind of to wrap up here, ICC Max really basically encompasses the complexity of color in the real world. It provides the ability to answer various questions about color. We can answer about what it is, how it's formulated, controller made, what does it look like, and how does it relate to or interact with light. And basically it provides a platform with real flexibility and extensibility for modeling and defining all sorts of different color workflows. Not necessarily a one-size-fit-all, but a really complete set for doing lots of color stuff. So with ICC Max, where are we now? Well, we have a standard defined by the International Color Consortium, and that can be found on the website iccmax.org. We are working on workflow-specific ICS documents. That's taking some time, and with that, that will allow implementers to basically define the specific subsets that they want to implement. We've been providing and promoting educational opportunities for developers. Last November we had the ICC Developers Conference that was very well attended, and people learned a lot. We're working on making the ICC Max an ISO standard. It's 20677 within the ICC, and it's making some good progress. I'm hoping in the next year or so it'll actually be an ISO standard. We have in addition to basically working on the standards, we also have an open source reference implementation available on GitHub, and individual companies are currently in the process of evaluating and implementing ICC Max features into products. Though there's really a lot to ICC Max, and deciding what you want to implement is going to take some time, and even Onyx Graphics is in the process of doing this evaluation, and hopefully sometime at the end of this year we'll have something that implements and provides ICC Max functionality. Here's some reference material if you really want to look and understand more about what I've kind of talked about in terms of the ICC webpage, the ICC Max page. If you want specific documents, you can go to there. The reference implementations on GitHub, and then I mentioned some of the stuff that I did in my PhD dissertation that provides some of the scientific background for doing things that can be done in ICC Max. And that's all I have. I'm open to any questions.
Well, thanks for the presentation today, Max. And in terms of questions, I have a couple things. First of all, I've talked to a couple of people who have had challenges in managing color on clear surfaces like glass or thin optically clear films that they're printing on. What are some strategies for addressing those?
Well, the first thing you need to do is you need to actually have something that actually going to measure spectral transmittance. If you try to use basically something like an I1 and put like white behind it and measure that, the challenge with that is that you're essentially, if you think about how the light transfer, the path of the light in terms of the measurement. You have the light coming from the device, it goes down, it goes through the colorant, hits the white paper, comes back to the colorant. So you're basically measuring how that colorant is affecting it twice, which, you know, on a clear surface, you're probably going to want to have something where the light only goes through once. Mm-hmm. That's probably the first and foremost thing you have. Another challenge you have with printing on those surfaces is you generally don't necessarily have really high ink load, and so you're going to be very have challenges with, you know, ink limiting and trying to get good saturated color at the same time as not necessarily having bad image artifacts, and that's not necessarily something simple or straightforward to do.
Okay. Next question. I know just from your presentation, there's been a lot of work on getting ICC Max together and sort of stepping forward in color. What do you feel like is the next step? I mean, this is, as we say, driving the future of color. Where are we going with this? Is there an endpoint that you think would be amazing to get to?
I think when we get to the point where it's actually implemented, I think the real key, the next point probably is going to be for specific industries where ICC color management, it doesn't really work well. I mean, in packaging, you know, you have a designer, they put things together, they're putting things in, they don't necessarily have a good way of previewing and seeing what they're going to get. And I think that the next step will be being able to do on-screen, 3D rendered previews to see an idea of what's going on, being able to actually do previews on various printers that have it, and doing repurposing. In the printing industry, going to 7 colors is actually an interesting thing that they're doing, and so I see that being an aspect of it.
Right.
Other industries are going, and I think the next step you're also going to see is you're going to see other industries that are going to be embracing aspects of ICC Max. You have the video industry that has HDR and issues with observer metamerism that are going to be addressed. But next steps we really have are basically finalizing specifications for interoperability conformance. From the ICC, the next steps are really getting ICS documents in place and having actual implementers actually implement to those.
Sure. Okay. Can you comment on, excuse me, on how ICC Max will help a printing workflow where managing color in both litho and wide format workflows will help toward matching color in both arenas?
In those cases, it's going to be the use of with the litho stuff, you have many more than just CMYK colorants, and being able to actually communicate about that. I mean, there are solutions right now that are in place that are proprietary, but being able to do that in a kind of cross-platform open way necessarily can't be done. And so that's probably where I see the how it can help there, is because we can actually communicate about those things much more effectively and get more accurate results. If you basically create an ICC version 4 profile and you're doing proofing of litho on a press, you're not going to be very satisfied necessarily, because you just don't have the accuracy in what you can encode in an ICC version 4 profile.
Okay. Okay. What would you say is the one bad habit that a lot of printing companies need to get over when it comes to color?
Not being attentive to the details of what they're doing and how it affects color. I think that you got to be focused on process control and doing things. If you really want to get good color, you have to actually be focused on process management. Some people will go and they'll get a media from anybody and then find a profile and assume that it works. And,
right.
And that really is basically, hoping for the best as opposed to doing color management.
Very good. Very good. Well, thanks again for the presentation today. That's all the questions we have.
Okay.
And thank you to all of you who joined us for today's presentation. We hope you found it interesting and informative for your business. And I do want to invite you, before we sign off, to take advantage of the 2017 SGI Expo, which is coming up October 10 through 12 in New Orleans. You can sign up now and get a register for a free Expo Pass at sgia.org, and we look forward to seeing you there. Also, we have an offering of other webinars on the website at sgia.org. They are here, they are free, and they're designed to help you make the best decisions for your company. So with that, thanks for joining us, and we look forward to seeing you on the line again soon. Bye-bye.